Welcome to The Explainer. Today, we've got a story for you about one of the most incredible revolutions in the history of science. We're talking about how a 2,500-year-old idea, the atom, the bedrock of reality, wasn't just challenged but completely shattered in the span of about 20 years.
You have to understand, for centuries, this was the absolute truth. The atom, whose very name means indivisible, was it, the final stop. It was seen as this fundamental, indestructible building block of the entire universe. Unchanging, unbreakable, the end of the line.
So what happens when a certainty that old starts to crack? When evidence pops up that just doesn't fit? Well, right at the turn of the 20th century, a series of totally baffling discoveries, from mysterious rays to impossible amounts of energy, began to unravel everything scientists thought they knew about matter itself.
And our story really kicks off in Paris, 1896. And like so many great scientific stories, it starts with a complete accident. A scientist was looking into one mystery and ended up stumbling upon something way, way stranger. Something that would blow the whole idea of the atom wide open.
And here's what's just wild, the speed of all this. I mean, look at this timeline. In just 2 decades, science went from noticing a weird glow in a desk drawer to completely rewriting the rules of reality. The pace of discovery was absolutely breathtaking.
Okay, so here's how it went down. Henri Becquerel had this theory that maybe fluorescent minerals could emit X-rays after being charged up by the sun, but by a total fluke, he left some uranium salts in a drawer with a photographic plate, and the plate got exposed. In the dark. The uranium was giving off these rays all by itself. This wasn't a chemical reaction. It was something coming from deep inside the element. He had just discovered radioactivity.
You'd think this would be front-page news, but it didn't really make huge waves at first. But it did catch the eye of a brilliant, incredibly determined chemist named Marie Curie. She had this gut feeling, this powerful intuition that if this energy was coming from the uranium atoms themselves, then this had to be a fundamental property of atoms. And if that was true, maybe other elements did it too.
And her genius was just this grueling, methodical persistence. She didn't just guess. No, she tested every single known element. She found that thorium was also radioactive. Then, she took on the backbreaking work of analyzing tons of ore to isolate 2 totally new elements, polonium and radium, which were millions of times more radioactive than uranium. Suddenly, the periodic table, which everyone thought was complete, had new members.
And this is where it gets serious. This wasn't just some lab curiosity. Scientists immediately grasped the enormous implications. The amount of energy being released was unlike anything ever seen before. The chemist Frederick Soddy gave this incredibly chilling warning, realizing that matter itself was a giant storehouse of energy. The game had just completely changed.
Okay, so let's connect the dots here. If atoms are spitting out energy in rays, then they can't be these solid little billiard balls. They have to have parts inside them. And just a year after Becquerel's discovery, a physicist over in Cambridge found the very first piece of that internal puzzle.
J.J. Thomson was playing around with these things called cathode rays, and he proved they weren't rays at all, but a stream of tiny negatively charged particles. But here's the absolute kicker. These particles were almost 2,000 times lighter than the lightest known atom, hydrogen. And, this is the crucial part, they were exactly the same no matter what metal they came from. He had discovered a universal component of all matter, the electron.
And that was it. That was the moment the ancient idea of the indivisible atom was officially dead. The question wasn't if the atom had parts anymore. As Thomson himself put it, the question was now, how is the atom built?
So, with the electron on the table, the race was on. It was a mad scramble. Scientists had to try and draw a blueprint for a machine they could never ever see. How do you arrange these negative electrons with the rest of the atom, which had to be positive?
Well, 2 big ideas went head-to-head. Thomson, the guy who found the electron, he proposed this plum pudding model, basically a blob of positive stuff with electrons stuck in it. But his student, Ernest Rutherford, came up with something way more radical, a tiny, dense, positive nucleus at the center with electrons orbiting it, like a miniature solar system, an atom that was almost entirely empty space.
Now, Rutherford's model was beautiful. It explained his experiments perfectly, but it had one huge, fatal flaw. According to every law of physics they knew, an orbiting electron would be constantly radiating energy. It should spiral into the nucleus and destroy the atom in a fraction of a second. His model, as brilliant as it was, just couldn't be stable.
So to solve this paradox, in comes a young Danish physicist named Niels Bohr.
And he basically says, what if the old rules of physics just don't apply down here? He proposed that electrons could only exist in certain special, stable orbits where they didn't lose energy. And to get from one to another, they didn't spiral. They made an instantaneous quantum jump. It was weird, it broke all the rules, but it worked.
And get this, at the exact same time, the physicists are tearing their hair out over the atom's structure. The chemists are facing their own separate crisis. The very definition of an element, a pure, unchangeable substance, was also starting to completely fall apart.
Okay, this next part is just mind-bending. Rutherford and his collaborator Frederick Soddy proved that radioactivity wasn't just energy being released, it was the atom itself changing its identity. An atom of uranium was literally, spontaneously turning into a different element. The ancient dream of the alchemists, transmutation, it was real, and it was happening naturally.
And for chemists, this discovery created absolute chaos. All of a sudden, they'd found over 30 new radioactive substances that all seemed to be their own unique elements. But there was no room for them in the periodic table. The entire system was on the verge of collapse.
The solution, when it came, was so simple and elegant. It was from Frederick Soddy again. He proposed the idea of isotopes, basically atoms of the same element that were chemically identical but had different weights. So you could have heavy lead and light lead, but it was all still lead. One simple idea, and it cleaned up the entire mess.
And just think about how radical that was. For over a century, one of the core beliefs in chemistry was that all atoms of an element were identical. And look at this. Here's J.J. Thomson, the guy who discovered the electron, stating it as a fact as late as 1914. With isotopes, that foundational idea was just gone.
So, okay, let's just pause for a second and take stock. In this incredibly short window, from 1896 to about 1916, the entire classical picture of matter had been completely demolished.
All the old certainties were just wiped away. The atom wasn't a solid little ball. It was a complex system, mostly empty space. Elements weren't forever. They could change into other elements. And an element wasn't just one thing. It was a whole family of isotopes. A new, dynamic, and frankly, much stranger reality had taken over.
And what's so cool about this story is that it wasn't just physicists in one lab and chemists in another. It was this messy, creative, powerful collaboration. You had a physicist, Rutherford, winning the Nobel Prize in Chemistry. You had a chemist, Marie Curie, winning Nobels in both physics and chemistry. The lines between fields had to blur because the atom itself didn't care about our labels.
And this is where we'll leave the story. The 2,500-year reign of the classical atom was over. But its death raised an even bigger, deeper question. This new atom, with its weird orbits and quantum jumps, it worked on paper, but it made no sense in the real world. This revolution closed the book on one era, but it opened the first, tantalizing and much stranger chapter of a whole new science, quantum mechanics.